Saxon Algebra 2, Lesson 1. You guys, you survived the horrors of Algebra 2 Lessons A and B. They are the worst lessons. They are my least favorite to teach in the whole program. It's a miserable way to start out the year, but now we're at Lesson 1, and we still have more than usual content, but it's nothing compared to those monsters. So breathe a sigh of relief that you've gotten past the worst of it, and let's go on from here. Let's talk about polygons. You've been talking about them forever. Let's not even bother writing it all down. Let me just show you. Polygons are straight-sided objects. They do not have lines that cross over each other. This is not a polygon. This is not a polygon because they cross over each other. This is not a polygon because polygons have straight sides, and this little ice cream cone is curved. So, not a polygon. It's kind of a hybrid, and we do a lot of problems that involve this combination of curved and straight, but they're not true polygons. They're hybrids. This is not a polygon because it's open. No, you have to close it. All right? Simple. These are all polygons. This one is called a concave polygon because it has this little cave in it. These are regular polygons, sometimes called convex. Equilateral means equal sides. Carrots just fell off my kitchen counter. That's kind of fun. Rolling around on the floor. Equilateral means equal sides, and those little marks show that each of those sides are the same length. Equiangular means the angles are all the same, and that's what those little curvy bits mean. One of the definitions of a convex polygon is that between any 2 points within the shape, you can draw a straight line, and the line will also be within the shape. Concave polygons are wacky because you can go outside of the shape in order to draw the line. I mean, nice to know. Nothing that's going to rock our worlds in the weeks to come. You can also classify polygons by the number of sides that they have, right? 5, 6, 7, 8. There are fancy names for them. We'll talk about triangles and quadrilaterals and pentagons, but after that, we just don't really worry about it that much. There is something called a regular polygon. I'm going to write this down. The word regular in geometry means that the angles within the shape are all the same, and the sides are also the same length, okay? So regular means it's perfect and even and equal in every way. This is a nice word to see in our problems. It makes us happy. Let's talk about triangles. We can classify triangles according to the size of their angles. This is a right triangle, and its main angle here is equal to 90 degrees. This is obtuse. You've heard this all before. This one has an angle that is greater than 90 degrees. And this is acute. And all of its angles are less than 90 degrees. Okay? No, the obtuse only has one that's so big. But you can only have one that is that big. It's not possible to do it any other way. Okay, the cool thing about any triangle, I'm drawing in an acute one, but it's all. They all have interior angles that add up to 180 degrees. Yay! Okay? So that's important to know for our problems. Now, this is when we categorize according to angle. We can also categorize according to the sides. And those go like this. There's equilateral, all sides the same. And we can demonstrate that with these little marks, right? Whenever you see, those are called tick marks or hash marks, we sometimes call them. With an equilateral triangle, they're all the same. Some triangles have two the same, but not the third. Oh, that's really crooked. It doesn't matter. It's called isosceles. Two sides the same. And then these are always really hard to draw because let's make it like that. I mean, I don't know how clearly that looks, but let me do this. That shows that all sides are different, and that's called scaling. Scaling. All sides different. Now, here's so that is the way we can describe the sides. Now, here's an interesting thing. There's a relationship between angles and sides. Let me flip. And the best way to illustrate this is with an isosceles triangle. For every angle, there's a corresponding side. It's the side opposite it. And there's a relationship between that angle and that opposite side. That's what trigonometry, a study we're going to begin this year, is all about. In isosceles triangles in particular, we know that these two sides are the same. So that tells us that these two angles are the same. Because oh, I don't even want to try to put this in words, you guys, because it's too complicated. But if we know that this is a 30-degree angle and this side is 8, and we know that this side is also 8, then we know that this must be a 30-degree angle because the matching sides have matching angles, all right? This is super useful in problems like example 1.1. We're told to find x and y. And we're given a triangle that looks like this. It's got the little tick marks there, and then it says y degrees, 50 degrees, x degrees. And you may remember this. We've done these before. What we're supposed to get from this is, oh look, these two sides correspond, they match. That's what those marks tell us. So, since sides and their opposite angles have a relationship, this one goes with this one goes with this one. If this one is 50 degrees, then this one also must be 50 degrees. So we can say x equals 50 degrees because their sides are the same, so the corresponding angles with those sides must also be the same. Cool. Okay, so this is 50 degrees. And so y, we also know that they all add up to 180, right? So if these two are 50, that equals 100. So this has to be 180 minus 100, or 80 degrees. Those are the right answers, okay? So we can start using our geometric knowledge to solve little algebra problems. Here's another one. With a fun picture, we're supposed to find x and y. It goes like that. This is called the reflex angle, right? It's the angle outside of the main angle. X degrees, y degrees, 40 degrees, and then we've got a B right there. In general, uppercase letters denote angles. Smaller case letters denote either unknowns or often they're used on sides, all right? So we have to figure out x and y. It always helps to go alphabetically or the order that John writes them in. So let's tackle x first. Well, we can't add up the 3 interior angles and subtract from 180 because we've only got one piece of information there. So those are both missing. But we see that these two angles go together to form a straight line. So we know that they are supplementary, right? So we know that this whole thing must be 180. And this much we know is 150. So x must be equal to 30 degrees. Because it's the outside. Cool. Okay? And then y, now we can use this rule because we know that y has to be equal to 180 minus the 40 that we knew in the first place, minus the 30 that we just figured out up there, right? Y minus 40 minus x, which is 30. So that is 180 minus 70. So y must be equal to 110. And that's right. Yay. Okay, so that's right. And I'm just going to write equals x down here because I always want to put my answers equal to the letters that represented them. Whenever that's possible, I want to do that. And I could have put a box around this whole thing, but that felt messy to me. So I just left my answer there and wrote that equals x down there. Okay, so there's another way we can use the geometric knowledge we have about triangles to solve simple algebra problems. Okay, we're buzzing through this lesson. We have two more problems left to do. So compared to last week, we're way ahead of the game. I'm gonna scoot down a little bit because the sun has come out and I don't want my page to be half in sun and half in shadow. That's just confusing. All right, part C, transversals. Those always remind me of vampires because Transylvania, right? Doesn't that sound like Transylvania to you? But these are not hard problems. They're actually kind of fun once you get their pattern figured out. They always start with a pair of parallel lines. This little symbol tells us that they're parallel. That's the beginning of, these are the conditions we need in order to create a transversal. If these lines aren't parallel, then forget it. Then what we do is we draw a line that chops through. Okay? This is the actual transversal, this line that cuts through the pair of parallel lines. And what it does is it creates a whole bunch of angles. You can see all these angles that it creates. And what's neat about them is that they have a very strong pattern to them. There will be a larger angle and a smaller angle. And then underneath the line, that pattern reverses. And then you get to the next parallel line, and it repeats itself. So this pattern allows us to draw a lot of information about the size of the angles, and it sets up some really neat algebraic problems that we can solve using this concept. Before we go on to those, I just want to show you that if you have a pair of parallel lines and you draw a transversal that goes straight through and cuts them all at a right angle, then all of these will be 90 degrees. We don't often see that, and it's one of those things that's so simple it's hard. That's kind of messy, but you can see that if this transversal comes through at a right angle, it's kind of boring. We like it better when it goes through at an angle and creates cool patterns. So here's an example. 1.4, we're supposed to find A, B, and C. We have a pair of parallel lines. We have those little arrowheads that tell us that they're parallel. John went ahead and named these lines for us, lines M and N, and then he karate chopped it. That's how I always think of transversals. They're a karate chop. This is C, this is B, this is 60, and this is A. Okay, so once again, a great strategy is go alphabetical and look at the numbers you do have to try to figure out how the actual numbers can help you. So here's A, and here's the only number we're given, 60. All right, Well, we know that these two have to add up to 180, right? Because this is a straight line, so this is a full 180. So these two guys must be supplementary. So A plus 60 has to equal 80. Yikes. So I'm going to subtract 60 from both sides. A equals 120 degrees. That's correct. Now, that helps us because we know that this must be the smaller angle. Oh, I'm sorry, 120. And this must be the larger angle, right? And we know that the values of those angles are gonna stay the same throughout this whole diagram. So all we have to do up here is go B. B is the larger angle, so that must be 120. And C is the smaller angle, so that must be 60. Remember, in any one diagram, the pattern will stay the same and those angles will all be the exact same measure. B equals 120, yes. C equals 60, yes. This is a good time for me to mention that when you're doing your homework, you know, some of these calculations you can do in your head. If they're super simple, I don't mind you doing some of it in your head, but you need to clearly label your answers. And whether you do that in the diagram or over to the side, that doesn't matter as much to me, as long as it's clear. All right. Are you ready? We have one more topic. I'm going to flip for this. And this is building on the idea of transversals. This topic is called proportional segments. And what happens is that we start with the parallel lines, only this time we're going to have 3 of them, and they're not equally spaced, but they are parallel. P, M, N. Don't ask me why he put them out of order. It doesn't matter. And instead of just having one transversal chopping through, we're going to have 2. They don't match in any way, but that's fine. We don't need them to. And what we're being given here, now instead of talking about the angles that are created in these lines, we want to talk about the lengths of these segments. 2, 3. Okay? What happens is that these segments are proportional. They bear a relationship to each other. So we can use either proportions or the scale factors to show that. And if I'm right that these are proportional, then 2 over 3 should equal 3 over 9/2. Let's cross multiply. 2, I'm going to put it over 1 because we're multiplying fractions there. 2 times 9 over 2 should be equal to 3 times 3. This cancels, and we get 9 equals 9. So that proves that what I said was right. These segments are proportional to each other. Let's try this with an example so you can see how the problems will work, but it's pretty much what I just did. 1.5. Okay. 3 lines again. Also named PM and N, also shown by arrowhead that they're parallel. And we have 2 transversals. And we've got some information about the lengths of the segments. This is 2, this is 5. This is, John does it like this, 8 over 3. All right, so he's showing you that's the length of this segment, and this is X. Do not let the creepy fractions scare you. As we saw last time, sometimes they sort themselves out quite nicely. So we want to solve for X, and all we have to do is set up our proportion. 2 over 5 equals 8/3 over x. Notice I exaggerate my fraction line so I can keep track of what's what. All right, I'm gonna cross multiply. 2x equals, and I'm just gonna multiply this in my head. 40 over 3. 5 times 8 is 40, right? And now I need to get rid of this 2. I want to divide by 2, but I can see if I divide by 2 over here, that's going to be a mess. So I'm going to use reciprocals instead. I'm going to multiply by 1/2, and then I'll multiply by 1/2 over here. This cancels. I'm left with the x the way I want it. I'm going to reduce this. I always try to reduce before I multiply. I like to make my numbers smaller before I make them big. So that all cancels, and I get x equals 20 over 3. So again, that's not a cute answer, but it's a correct answer. And it represents the length of this segment. Remember, with proportional segments, we're talking about the length of the segment and not the degree of the angles anymore. We've switched our focus. Okay, ta-da, that's lesson 1. It was hideous, but nowhere near as gruesome as A and B. You are now all set to do. Now we're going back to our regular format. Last week was weird, but this week you're going to get videos for 4 lessons. Right, this is the first one. You're going to get 1 and 2 at the same time. You'll watch the videos separately. You'll do the homework separately. The first day you'll do the practice plus the odds. Okay? No more doing the evens. We're done with that. Let's just call this Monday. You might not do it on Monday, but let's just say. On Tuesday, you'll watch lesson 2. You'll do the practice plus the odds. And then let's say on Wednesday and Thursday you're going to do your other ones. But now we're just doing the same thing every day. All right? So we've had 1 week that was wonky where we were doing odds and then evens. Now we're on our standard groove, which will look like this. Okay, my work here is done. I will see you for lesson 2, and we'll get into some actual, we're gonna do some geometry still, but there'll be some actual algebra heading up in there, so. All right, good luck, thank you, goodbye.